Assalamualaikum warahmatullahi wabarakatuh, and hi. Today I will going to present Mechanical System Design 2 with the title of Development of Internet of Things Monitoring System for High Yield Production in Palm Oil Plantation. I will be represent Group 17 with our supervisor Sir Muhammad Faizari bin Muhammad Noor, and we have 5 members. Which is me, Ahmad Zaimul Adli, and then Muhammad Shafiq, Muhammad Faiz, followed by Muhammad Hafiz, and finally Muhammad bin Muhammad Jufri. We will be representing the contents as follows. First, we will do introduction. After that, background, followed by problem statement. After that, objective, and then equipment sizing and drawing. After that, PNID. After that, engineering analysis. After that, costing, and then followed by project management, and finally we will go through the conclusion. Okay, we will go to the introduction. We will go through the point one by one. Okay, first, palm oil harvest is large, and Malaysia consists of 46% of the overall yield. This is based on the 2011 report, which state exports of palm oil and palm kernel of the world reached almost 39.04 million ton, in which 46% of it were Malaysia's share. This is due to Malaysian manufacturers have installed the most efficient refining and fractionation facilities to add value for crude palm oil. After that, palm has the highest produce of edible oil yield compared to alternatives, which is 5 to 8 more times more yield. After that, this project aims to increase the production of the yield up to 40% with the assist of the Internet of Things. This is where the Internet of Things come to play. We will use it because it hypothesized that the palm oil production will increase with the help of Internet of Things, which results in, we hope, to higher the export rate. After that, we will practice the Internet of Things by covering various plantation aspects such as water flow, pesticides, pH value of soil, air quality, and weather. The data collected will be analyzed by the operator for better management control. Okay, we will go to the background. We have about 3 points here. First, Malaysian Palm Oil Council (MPOC) states Malaysia producing 28% of the world palm oil production and contributing about 33% of the world export. By our project, we will be introducing Internet of Things that may assist in increasing the yield. And then the project is proposed in a physical place, which is a palm tree plantation at Ladang Gelung Pepuyu, Perak, under the agency of Perbadanan Kemajuan Ekonomi Islam Negeri Perak, which shorts for PKEINPK. Okay, for the problem statement, we have about 3 problem statements that we will go through together. Okay, first, local palm oil production has potential to be more effective, which is true, because in the consecutive year, we see in the plantations such as Samdarbi has increased its production year by year, which means there are still more room. It's still more room to emphasize to become more effective in producing large yield. Okay, and then after that, if not maintained effectively, it will affect the rate of yield produced, which is true because the palm tree is sensitive towards its environment, which is, if it's not ideal, and then it will affect the rate of yield produced. So we must always keep the palm tree in an ideal condition. Okay, then for the aspect that we identify that affect the health of the palm tree are: first, soil pH value, and then pesticide, followed by irrigation, and then fertilization, and finally fertigation. Okay, this is the aspect that we identified that affect the health, and we will cover it by using our interested Internet of Things. Okay, for the objective, we have about 3 also. First, to identify the parameters that increase the yield of palm oil production. The parameters will be established by doing researches not only through published articles and journals, but also we suggest first by interviewing agriculturists and engineers that directly and indirectly involved in palm oil plantation. But since we are amid of COVID-19 pandemic, all interviews will have to be done through online platform. Okay, for the second objective, it designs suitable agricultural IoT system for palm oil plantation. This design project is constructed based on the existing ladang gelung pupuyu, as I said earlier, as our datum and benchmark. Our design concept of IoT system will be established so that it acquires with the parameters and condition of ladang gelung pupuyu. The design process diagram will be formulated later throughout the project. Okay, after that, finally, we will go to the final objective, propose monitoring features and cost of the IoT system. Our last objective is to propose monitoring features and cost of the system by applying the morphology chart. The chart composed of several alternatives for IoT system in which later it will be evaluated by pure metrics concept in pure chart to determine the best concept design of on IoT for the oil palm plantation.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hafiz, and I'll be presenting the equipment specification for the system. Um, these are the list of equipment that I'll be presenting today. The first one is high precision soil nutrients. This equipment is to detect soil condition, and then the NVI sensor or green seeker for the detection of leaves color, and then Agras MG1S for the pesticide. Next, robotic smart farming for the fertigation system, and then smart IoT fuzzy irrigation system for the irrigation, and finally the centrifugal pump, the only mechanical equipment that present in our system. So for the first equipment, it's the high precision soil nutrient for the soil condition detection. So this equipment is easy to measure, not only for professional but also for non-professionals. Just insert the instrument into the soil to measure. IP68 grade, waterproof and dustproof to ensure the normal operation of components for a long time. Good sealing performance to prevent moisture from entering the interior of the instrument. The length of this equipment is 11.5 centimeters. The width is 4 centimeter, weight 203 gram. And the measuring range is 0 until 199 mg per kilogram. As for the power supply, it is 12 volt until 24 volt direct current. Next, NDVI sensor or green seeker. This equipment is to the detection of leaf color. So the sensor emits brief bursts of red and infrared light and then measures the amount of each type of light that is reflected back from the plant. The strength of the detected light is a direct indicator of the health of the crop. The higher the reading, the healthier the plant. So for the spec is that the battery is 3.7 DVC nominal and current 1130 mAh. As for the dimension is 9 centimeter times 27 centimeters. The weight battery for this equipment is 310 gram, including battery. And the weight of this equipment is 310 gram, including battery. For the field of view that will be covered for the sensor, 10 at 24 or 20 at 48. Operating height 24 inch until 48 inch. Next, the Agras MG1S. This equipment is for the pesticide control. The radar sensing system that provides additional reliability during flight. The spraying system and flow sensor ensure accurate operation. This spraying system is the system that will be used to control pesticide. The dimension of this equipment is 1471 millimeters times 1471 millimeters times 482 millimeters. The liquid tank volume, which is the liquid for the control of pesticide, is 10 liter or 10 kg. The quantity nozzle for the spray of fluid from the tank, it contains 4 nozzles. The nozzle model is 0 0.379 liters per minute. Total weight of the equipment is 23.8 kilogram. Max power consumption 6,400 watt. Hovering time 22 minutes for 13.8 kilogram, but only 10 minutes for 23.8 kilogram. Max flying speed 13 meter per second. Max transmission range 1 kilometer, and as for the battery capacity is 9,000 mAh. Next, robotics smart farming. This equipment is for the fertigation system. The robotics empower farmers with more control and information on the crop. This enables farmland level real-time information to control field-level processes and equipment. Real-time automation, water pump, irrigation sprinkler, fertilizer, ventilators, fogger. GIS and map-based search track and predict cropping details. As for the farmer management, it uses digitalizing documents. As for the agri-input management, assist in disbursement and procurement of crop. Moving on to the next equipment, the smart IoT fuzzy irrigation system. This system is for the irrigation system as stated above. It uses low cost off-the-shelf sensors and actuators for continuously monitoring environmental conditions of arable areas. Air temperature, moisture, and soil humidity are continuously monitored, making three parameters to be to be measured and monitored. As input for that algorithm has the air humidity and temperature and the soil moisture from multiple ground humidity sensors. With the help of servo valve, the ground humidity is controlled. This is the centrifugal pump. The centrifugal pump used to pump the fertilizer fluid out of the tank for the use of this system. The average speed is 1,480 RPM. The max capacity is 300 liters per second. Max head of this pump is 150 meters. Maximum speed is 3,500 RPM. Diameter of the impeller will be reduced. As for the max working temperature is 105 Celsius. And finally, for the working pressure, generally it is 1 megapascal. It can rise to 1.6 megapascal if material is nodular cast or cast steel. This is the orthographic drawing of the centrifugal pump. So the dimensions here are all in centimeters. This drawing consists of the centrifugal pump itself and also the motor that powers the centrifugal pump. And I think that's all from me. Thank you.
Alright, let's moving on to the next part of presentation, which is piping and instrumentation diagram. In this section, I will explain the working principle of each of every system, and I will show how all the components integrated together to form a complete IoT monitoring system. The first system is smart fuzzy irrigation system. This system is functioning to irrigate the plant using a sprinkler by analyzing the soil humidity. Several humidity sensors are placed around a tree to increase the precision, and the reading data by the humidity sensor is then transmitted to MCU to analyze and determine the exact amount of water needed by the plant and pass the information to the server for further action by the plantation owner. And also we have control valve with the help of flow element. It restricts the water that pumping out from the tank to ensure the plant are not over or lack of water. Next, let's take a look on piping and instrumentation diagram for robotic smart farming. The system focuses on monitoring the heat, pH, and salinity of the soil. It uses the same preliminary equipment as smart fuzzy irrigation system, and as it is the extension of irrigation system. And also because of that, robotic smart farming is integrated together with smart fuzzy irrigation system, and as the result, it gave the most accurate result of the current state of the soil for better analyzation. This component, the component in this component include first uh, heat sensor to detect the heat, pH sensor to detect pH, and lastly EC meter to detect the salinity inside the soil. Third is NVDI sensor with drone. The function of the system is to monitor the health state of a tree based on its leaf color. So user has a full control over the drone that attached with a detachable NVDI sensor. The sensor will detect any leaf that lack of nutrient and transfer the information to MCU for processing and analyzation. MCU transmitted the data to cloud server for visualization and monitoring via Wi-Fi signal for the plantation owner. Lastly is DJI Agras MG1S. So this drone is used to spray pesticide on palm tree shoot to avoid from being eaten by insect. The drone is attached with spray system and flow sensor that control the volume of spray to ensure accurate and efficient operation. Also, leveling sensor in MG1S help the drone to adjust its height so the spray even reach the lower part of plant and underneath the leaf. Lastly, all file systems sending their information to a server via a Wi-Fi signal. The server is a platform that store all the data and transform it into understandable information. It gives a direct access for the owner to monitor the plantation through smartphone anywhere, anytime. In conclusion, this system consists of 5 components for exactly 5 main reasons. First is for irrigation. That's why we have smart fuzzy irrigation system. Second, to monitor the soil condition, which is covered by robotic smart farming. And thirdly, for fertilization, which is handled by DISO high precision soil nutrient. And fourth is to monitor the leaf color, which is done by the NVDI drone. And lastly, for pesticide, which is perfectly handled by DJI Agras MG1S.
Assalamualaikum. My name is Muhammad Faiz Zainal and I'll be talking regarding the engineering analysis which will be conducted on each of the items for our physical decomposition. So for the first one is the NDVI sensor, which is to measure the leaf color. NDVI, which stands for Normalized Difference in Vegetative Index sensor, is a handheld device which uses light-emitting diodes to generate red and near-infrared light, which are used to calculate NDVI values. It is based on a simple principle that red lights absorbed by chlorophyll on the plant as an energy source during photosynthesis. So therefore, healthy plants absorb more red light and reflect larger amount of NIR than those that are unhealthy and results in a higher NDVI values. So for our project here, we assume that the NIR reflected is 0.5 and the rate reflected is 0.08, which results in NDVI value of 0.72. And also for this sensor, the power generated is calculated, which result in 0.60625 ampere, and the energy, which uses the formula of power times time, so 2.5 watt times 1 hour, which result in 2.5 watt per hour. And next will be the pesticides, which we use the Agras MG1S drone to provide the pesticide control in our palm oil plantation. So for the power output uses by the drone, which calculated by E out equals to current times voltage, as we always know, which result in 3,800 watt. So to determine the area of the propeller by the drone, we use the area formula pi d square over 4. If the diameter of the propeller which we receive from the catalog is 0.5334, and by using the formula, the swept area created by the propeller is 0.223 meters square. So the power of the wind, which is calculated to ensure the efficiency of the drone, is determined by this formula: half the times density of air times air swept area by the propeller times the velocity of the wind. So the velocity of the wind is 2 meters per second, which we receive based on the monthly mean wind speed at Ipoh, Perak, in a literature review, which was stated in the progress report. So the power of the wind is 1.0927 watt. And the overall efficiency, which is useful power output divided by the total power consumption. The total power consumption, which is 6,400 watt, based on the description of the DJI in the catalog, and hence the overall efficiency is 0.594. Furthermore, for our fertigation, physical decomposition, which we will be using the smart fuzzy irrigation. So first of all, to determine the overall efficiency, we calculated the area of the pipe, which uses your typical area formula, which we have learned in many sub courses. So, and also next will be the mass flow rate, which is area times velocity times density, which we learn in fluid mechanics, and we apply here. So the mass flow rate for this system, the smart fuzzy irrigation system, is 1.6 kilogram per second. Then from the mass flow rate, we will convert it to the volumetric flow rate, which will result in 0.001601 meter cube second. Next will be how much power does the pump needed to use to allow the flow rate move in all of the plants in the plantation. So the pump input power, which is equals to density times 9.81 gravitational acceleration times flow rate times head. So for the head of the pump is assumed to be 2 meter for this system, and also the pump efficiency is assumed to be 0.8, since most of the pumps efficiency required to be 0.8 to be effective. So the pump input power is 39.27 watt. However, what will be the output? In order to get the efficiency, the power output is needed to be calculated, which is by using the formula density times gravitational acceleration times flow rate times head. This is without the pump efficiency. So we have calculated. It turns out that the pump power input is pump power output. So my bad, this is a typo. 31.42 watt. So, however, we needed to know the motor efficiency that is required to allow the pump to operate, which is 0.7457, which is it is a constant to to convert the horsepower into watt times horsepower times load and divided by motor power input. So for this motor in our system, we have assumed that the horsepower is 4 horsepower and load it will be 0.25 kilowatt a kilonewton, and the motor power input is 0.91 kilowatt. This is from the description of the motor that we have selected. So the efficiency of the motor is 0.81. So the next one will be the overall efficiency of the whole smart fuzzy irrigation system. We calculated by motor efficiency times pump efficiency, and it is 0.66. So for the next one will be robotics smart farming. It is to calculate the soil. It is to measure the soil condition. So first of all, we use the Darcy's law, which describes the flow of a fluid through a porous medium. As we can see at the right side of the slide, we've shown the picture of a typical Darcy's law. So the next formula we'll be using the Green and M model, which is useful as a conceptual model for physical processes of infiltration. And below of this formula is the parameters that are needed to calculate. So some assumptions are needed to be made in order to make the calculation. For example, the soil is silty, and below are the assumptions such as the porosity, suction head, hydraulic conductivity, and also the effectiveness of the saturation, which is this one. So based on these two equations, Darcy's law and the previous one, we can calculate the cumulative depth of water infiltrated and also the rate of infiltration for every 0.25 hour. So here is the cumulative depth water infiltrated and rate of infiltration. Hence, the power consumption can be calculated, and for this system, we can assume the head pump, the flow rate, the voltage, and also the current to calculate the efficiency. Lastly, the efficiency is 0.9781. For the fifth physical decomposition, which is to calculate the fertilizer or monitor the fertilizer. So there is no power is needed to calculate the fertilizer physical decomposition. So below here are the micronutrients that are needed to use for the palm oil plantation, which is gained from literature review. And if we assume the stock solution or the vessel, it is 100 liter. So we can assume the ppm, particles per million, that is needed for each of the element, such as N, P, K, Mg, Ci. N is for nitrogen, potassium, and so on. So as we can see, the potassium is the most needed for the palm oil plantation. So for our final decomposition, this will be our choice, which is DG for our networking. And if we assume that our palm oil plantation will be operating in a year, hence the yearly cost of our networking is 3,240 ringgit. And that is all from me. I will pass on my presentation to Mol for the costing part.
Okay, so for the costing part, first we will go through the assumption first. Okay, there are about 5 assumptions. First, regarding limitation of projection, the financial projection is done based on values depicted in the revenue section, which produces expected assets, liabilities, capital costs, and expenses. After that, for the sales cost aspect, based on our objective of this project, which is to increase 40% of global yield production per hectare, the average crude palm oil CPO production per month per hectare is 3.5 metric ton. This is what is our our target. Raw material, this will include expenses relating to water, pesticides, and fertilizer use. After that, our assumption is for the overhead cost. Number of workers in the palm oil plantation is expected to be 10 personnel, and an increase of 2% for their salaries each year. After that, production projection. Ladang Gelumpuyu area is 450 hectare. The price of CPO as of March 2021 is 3,928 ringgit per metric ton. So this is our initial assumption. Then we will go to the cash flow. The cash flow projection is the estimation to indicate money flowing in and out of palm oil plantation, and a monthly projection over a period of 4 years is done. Okay, so as you can see here, this is the first year of the cash flow. The blue bar is the cash flow, and the orange bar is the cash balance. Okay, don't worry, we have the table of the values and everything in the appendices, which will be also present later throughout the slide. Okay, this is for the year 2, the year 3, and then the year 4. Okay, so this is basically a randomized number. So this is how we get the distribution lah. So we get the revenue, we get the sales and everything, and then we will distribute. So this is how we get. This is the projection only. Okay. After that, we will go to the break-even analysis. Break-even analysis is a measure to estimate the targeted sales amount, assuming a fixed variable which are unaffected by the number of revenues, and cost variable depends on income directly. By estimating this value for over the period of 4 years or 48 months, the point at which the plantation made neither profit nor loss, break-even, can be obtained. This figure shows the break-even analysis of the plantation, which is about 1.5 months, as you can see here lah, based on the assumption that I stated earlier. Okay, next for the costing, we'll go through the projection of profit and loss. The following figure shows the projected profit and loss presentation for the course of 4 years, 2021 until 2024. From the projected profit and loss chart for the first 4 years, it is estimated that the plantation will face some losses on the first 2 years and will start generating profit only after the 3rd year, as you can see from the graph. Okay, alright. Okay, this is the costing appendices. As you can see here from the table, this is from our previous projection of profit and loss. This is what is referred to lah, this table. Okay, after that, this table regarding our projected cash flow. This is how we get the bar in the cash flow slide, which is from this table, which we generated from our projection.
Assalamualaikum, and my name is Muhammad Shafiq, and I will proceed with project management. So here is an organizational chart. The project supervisor for our project is Faizari. He acts as a supervisor to supervise the project and make sure all the tasks are performed throughout the project. As for team leader, Zaimul has been appointed to lead the project. He handles the meeting and responsible for developing and implementing the timeline to make sure the objective of the project are achieved. Next, Shafiq is a person in charge of planning, which is planning engineer. Planning engineer help the team deliver project by providing a guidelines and schedule for work. He develop strategies determine material and labor costs, monitor crew performance, ensure health and safety regulations are obeyed. Meanwhile, Hafiz held a role as mechanical engineer, where he designed and tested the system installed and made sure all the components of subsystem work properly. As for Faiz, he has been appointed as a control engineer to perform a role in designing and developing the system to be installed. Lastly, Muhammad as a structural engineer, he also involved in providing the main design and PNID for the system. He makes sure all the structures are safe and capable of working in the palm oil plantation. Next, the project scheduling are shown as above. The list of the activities involved all the activities from day 1 until the handover day. If you can see, there are a gap in week 13 until 16 where we took a break for a project. The project then proceeds until it is finished. And here is the second page of the Gantt chart, and where we can see the next execution of storage tank, control valve, and also pump. And proceed with the second subsystem, which is commissioning of smart fuzzy irrigation system until the testing of smart fuzzy. The Gantt chart provides all the timing for the installation of the system. You can see that all the system has the same pattern since the project has been performed as planned. Most of the education part are performed on the same week according to the Gantt chart provided here. And we proceed the activities or work with the commissioning of robotic smart farming system, which is the last subsystem. And then after we finish the installation of all the system, we integrate the IoT subsystem to the server, and then we install the IoT system into the subsystem. And finally, we inspect all the subsystem and the integration of the system to make sure that all the system working properly before we hand the project to the client. From the list of activities, that also the same list we use for Gantt chart, we are able to form a immediate predecessor, or also known as WBS, work break-even structure. So from here we can see the immediate predecessor of all the activities and the duration of the day, on how long we took for us to finish each activities or work. In this list, we provide all the main activities that must be performed to make sure that the project can be performed successfully. And to make it easier, we divide the table according to the subsystem to make sure that we can see the difference between the system and another system. All the activities are included inside the immediate predecessor, uh, including all the installation of subsystem until the integration of IoT subsystem, final inspection, and handover of the project. From the predecessor list, the activity on nodes AON are established. Here is overall AON for this project. From this note, we can see which activity must be fully completed in order for another activity to be done. In this AON, we can see how long for each activities are taken to be completed. From the activity on nodes, we can see the critical path of the project. This critical path shows the sequence of work where all of this work must be performed to make sure that the project can be a success, especially the activities in the middle. This critical path is the longest path of activities performed for this project. And so I think that's all for project management, and I will proceed with the conclusion that can be made from our project. As for the conclusion, we believe that we are able to increase the yield of the production of palm oil plantation after we implement the IoT system into the plantation. So we believe we are able to design the IoT system that can help to improve the system inside the plantation. Most of the new system use the new technology, and we believe and the system can help to improve the yield of the palm oil plantation. Compared to the old method, most of the IoT system use a new technology, and it is expected to increase the yield production after 4 years, where the profit will be double or triple the current profit. So as for the profit, we expect to achieve the profit after 2 months according to break-even analysis, where we can say we are able to get all the money used for this project after 2 months of the implementation. So the overall conclusion is we believe that we are successfully overcome all the limiting factors for the year production by establishing this new IoT system. So I think that's all from us. Thank you. Assalamualaikum.